So this section is a review of descriptive statistics for regression. So this is when we have two quantitative variables. We're going to start with thinking about the correlation coefficient, which we denote R. The correlation coefficient summarizes the strength and direction of two variables, x and y. And it specifically tells us about the linear relationship between two variables, x and y. We're going to call x our explanatory variable. And we're going to call y our response variable. The correlation ranges from -1 to +1, and if there is no linear relationship, r is equal to 0. So that means that 0 is right in the middle of the range of correlation. And so if we have a correlation of -1, we have perfect negative linear association. And that means that we would have a plot that looks something like this between our two, it's got to be linear, between our two variables. It could also look something like this. So still linear between our two variables, maybe a different slope. Similarly, if r equals +1, that means we have a perfect positive linear association between our two variables x and y. And if we were to plot that relationship, it would look something like this, where all of our points fall exactly along a positive sloping line. Or it could look like this, where again, all of our points are falling along a positively sloping line, but we just don't know what that slope is. So the correlation tells about the strength and the direction. So in this case, the perfect is the strength, the direction is positive. It just doesn't tell us the slope. It does tell us, however, about that linear association. So if there's no linear association, the correlation equals 0. So here are some examples of what that might look like. We could just have a cloud or a mass of points. And in this case, there's no clear linear association or even no association at all. And so here there's no linear association. It could be something like this, where there's no relationship at all because x doesn't change. It could also be like this, where there's no relationship because y is now a constant. And so as x increases, y doesn't change. Or to really emphasize that it's about the linear relationship, here we have x and y both changing, but it's that there's a non-linear relationship. So as x increases, y first increases, but then decreases. And because this is non-linear, the correlation is 0. So these are four possible, of many possible examples where we would have a 0 correlation. So the correlation coefficient only tells us about linear relationships. It does not pick up nonlinear or curved relationships. And it does not pick up relationships but it could also give us the same result, a correlation of 0, if we have a cloud or if there's no variability in one of the variables. Related to the correlation coefficient is the coefficient of determination, r squared. And the coefficient of determination is a proportion, and it's the proportion of variability of the response, y, explained by the model, and that's where our x variable is contained. If the r squared value is close to 1, the regression line provides very accurate predictions, and that means the model explains a lot of the variability in the response. If the r squared value is close to 0, however, the regression line is not very useful in making predictions, and the model does not explain much of the variability in the response. So we have some sort of related ideas. If the correlation coefficient is close to +1 or -1, we have a strong linear association, either positive or negative, and that would also tell us that the r squared value is close to 1, providing pretty accurate predictions. If the correlation, however, is pretty close to 0, then that means the r squared value is close to 0, If we have a weak linear association because the correlation is close to zero, then the model is going to do pretty poorly in making predictions, and we'll have a r² close to zero. Now the correlation is not the same thing as the slope, and I already drew a couple of examples like that, but here I'm going to try to solidify that idea even more. So I've provided 4 plots, 1, 2, 3, and 4, with different correlations and different slopes. I would like you to take a minute, so you can pause the video, to compare the slopes, compare the correlations, see which ones are similar, see which ones are different, and see if you can come up with an idea for which plot you like the best, which one you like the worst, and a justification for why. I hope that you picked plot 2 as your favorite. But let's compare these plots first. Plots 1 and 2, so this first row, have the same slope. This slope is what we might think of as the effect size. That effect, which we've talked about, is the change in a response. So relative to there being no relationship at all, how big is the change in the response, or the change in y, when we move along the x-axis? And here we see that as we move 1 unit in x, we get a fairly sizable change in y. And anytime we move 1 unit in x, we get a pretty big change in y. So that is our effect size. How big is the change in the response? How big is the effect on y as we move along the x-axis? But we like plot 2 better than 1 because there's less variability in the data around that line. And that means that plot 2 has a high correlation. Our correlation here, R, is close to 1. In plot 1, the correlation is around 0.5. There's a relatively weak correlation, and that means we've got more variability of these points around the line. So even though both plots 1 and 2 have the same slope, a relatively large effect, we prefer plot 2 because there's less variability. We can see that effect more clearly. Now let's look at plots 3 and 4. These also have the same slope as each other, but it's a smaller one. So there is a small effect. As we change 1 unit in x, there is a very small change in y. In fact, it's hardly even noticeable. But there is an effect that is not a horizontal line, it is not a flat line. So as we increase x, there is a response. It is a change in the response. But if we look at plot 4, because of this high variability around the line, that is, because of that low correlation between these two variables, there's a lot of noise, so it's hard to see what that effect might be. In plot 3, there is a high correlation. And in fact, this correlation is pretty close to 1, just like we saw in plot 2. These correlations are both in the high 0.9s. And in plot 4, just like in plot 1, these correlations are around 0.5 or even lower. So plot 2, we have a large effect, a big slope, and a high correlation. In plot 3, we have a very, very small slope, a very low slope, and a high correlation. So we can see the effect of x on y more clearly in plot 3 than in plot 4 because of that tight clustering or tight scatter of the points around the line. The bigger the variability, or the smaller the correlation, the harder it is to see that effect. With regression, we might ask some questions, such as, is there an association or is there a relationship, specifically a linear one, between two variables such as car weight and gas mileage? In this case, car weight is going to be our explanatory variable x, and gas mileage is going to be our response variable y, and they are both quantitative variables. We're going to focus now on using the plot and that summary of fit table. First, let's look at this plot. We're going to interpret it and describe this relationship. And when we look at a scatter plot, there are four things that we describe. We describe the form, the direction, the strength, and we look for any anomalies that may be present. And we'll take each of these in turn. In terms of the form, we're asking, is it linear or nonlinear? In this case, this is a linear form, and we can tell that it's linear because, first off, there is a line, but if we ignored this red line, as x increases, as the car weights increase, the mileage tends to decrease at about that same rate. So there's no curve or any like tapering off. In terms of direction, we're going to say this is negative. So really we're looking at the slope. And that comes from saying, again, as car weights increase, the mileage tends to decrease. So this is a negative association. We can think about it this way too. So cars with above average weight tend to have below average miles per gallon. Now that doesn't mean that all cars with high weights have or always will have low mileage. This is just the general trend or state of things. In terms of the strength, visually, it looks like there's a fairly strong relationship. All the points are fairly clustered around this imaginary line. So there's a moderately strong relationship. We can support this numerically, and so there are three things that we will look at. We're going to look at the r squared, we're going to look at the correlation coefficient, and we'll look at this mean squared error. The r squared is provided up here in the summary of fit. Our r squared is 0.751. That means 75.1% of the variability in mileage can be explained by the model with weight. So when we use weight to predict mileage, we explain 75.1% of the variability in mileage. So that's doing pretty well. We can also find the correlation coefficient. So if r squared is 75.1% or 0.751, the correlation coefficient is the square root of r squared. So this is how they're related. I can take the square root of 0.751 and I end up with 0.867. But if I left it at that, this would tell me that there is a positive linear relationship between weight and mileage. And we know that's not true by looking at this plot and by looking at our slope up here. So this is actually negative. So remember, when you take the square root, there's a plus root, a positive root, and a negative root. And so we have to use the context of our plot and our fitted line to identify whether this should be a positive or a negative correlation. So this is telling me that there is a strong negative linear association between car weight and mileage. Finally, we can use this idea known as the root mean squared error. And this is also denoted the RMSE. The RMSE, this tells us the typical difference or distance between our predictions and what we've observed. In this case, the RMSE is 3.016, meaning that our predictions are off by 3.016 miles per gallon on average. So let's interpret this slope. Our sample slope here is b equals negative 0.0052, and I'm going to leave it there just so that we're not dealing with too many decimal places. This is saying as weight increases by 1 pound, the predicted mileage of cars will decrease by 0.0052 miles per gallon on average. So let's break this into its pieces. So as weight, this is my explanatory variable x. And we're saying as it increases by 1 pound, so that would be 1 unit, because we're only ever going to take this 1 unit at a time. The predicted, because this is my sample data, so this is only telling me about what is predicted to happen, not what is truly going to happen, because this is only based on a specific sample. And the next time I go out and get a sample of 25 cars, I would get a different equation because my statistics would change. The predicted mileage, so this is my response variable y, and it's going to decrease because I have a negative slope by 0.0052 miles per gallon, and that's my value there. So all of this is based on the context and the specific value of my estimate of my sample slope. Let's look at my sample intercept. A equals 45.645. In this case, I interpret the y-intercept the same way I would in geometry, for example. So, for cars that weigh 0 pounds, the predicted mileage is 45.645 miles per gallon on average. So we can do this again. So for cars that weigh 0 pounds, so this is my explanatory variable x, it's always plugged in at x equals 0. The predicted mileage, so this is my response variable y, and this is my value of a. Now let's think about it. Does this make sense? This does not make sense. This is in fact nonsense for a couple of reasons. One, no cars weigh 0 pounds. That's impossible. But it is a correct interpretation. The problem with this is that it is an example of extrapolation. Let's look back at our data. Here we see that the smallest value is 2,000 pounds. So the lightest cars in our sample are about 2,000 pounds. They're actually around 2,500 pounds. And we're trying to predict for something way smaller than that, 2,000 pounds lighter than that at 0. The model does not know how to handle things outside the range of our data set. That's an example of extrapolation. So it's going to think that everything just keeps going on all nicely, nice long line like this, and yet we know that cars don't really weigh less than maybe 1,000 pounds, maybe 500 pounds if you're like in a dune buggy or something like that, but there are no 0-pound cars. So it's up to us, the smart statistician, the smart user, to know when to stop. So let's look at this again. So we're saying that as weight increases by 1 pound, the predicted mileage of cars will decrease by 0.0052 miles per gallon. That's fine. We usually don't weigh cars in exactly pounds weight. So let's think about what if we weigh in tons. What happens to our slope and what happens to our intercept? The slope gets bigger. In this case, farther from 0. And in fact, we can just take our slope and multiply it by 2,000. Because there are 2,000 pounds per ton. And so instead of saying as weight increases by 1 unit, being 1 pound, we're really saying what happens as weight increases by 2,000 pounds, which is our new unit. So instead of having this tiny little incremental change in y, we're going to have a huge change in y. So our slope is now going to be 10.4 miles per gallon per ton. So for each new unit increase in x, for every 1 ton increase in the mileage of a car, we predict the slope to increase, or the mileage, for every 1 ton increase in the weight of the car, excuse me, I keep getting these variables confused. For every 1 ton increase in the weight of a car, we predict the mileage to decrease by 10.4 miles per gallon. And that is easier to interpret. It's hard to understand or to think about 5/1000ths of a mile per gallon change. It's easy to understand a 10.4 mile per gallon change, just as it's easier to understand a 1 ton change in the weight. So let's use this line, because it's one thing to kind of think all esoterically about this general relationship. Let's use the line to predict for a specific car. So the Mercedes-Benz SLR has a weight of 3,220 pounds. It has a mileage of 22 miles per gallon. Pause the video and get the predicted mileage and determine whether the model is doing a good job and how the model is doing in terms of predicting that mileage. What I've written here are the 2 possible ways that we might write our prediction equation. Y hat equals 45.645 minus 0.0052 times x, or MPG, miles per gallon, hat equals 45.645 minus 0.0052 times weight. Either way, we're talking about a prediction equation. So this little hat is telling me I'm talking about the predicted response. So this is not saying this is what I actually observe. This is saying this is what my model is predicting when I plug in a specific value for my explanatory variable. So let's see how we do this. We're saying that the true weight for Mercedes-Benz is 3,220 pounds. So I'm going to plug that into my model for the explanatory variable. So that'll be 45.645 minus 0.0052 times 3,220. When I solve for this, my predicted mileage for this particular car is 28.83 miles per gallon. So this is just what I predict. The actual mileage is 22. So I'm not exactly right. In fact, I'm off by about 6.83 miles. So what I'm going to do is I'm going to find my residual. This is my prediction error. How wrong I was in predicting. So to find my residual, I take what I actually observed, I subtract off what I estimated, or my prediction, and so that will be 22 minus 28.83, and I get that negative 6.83 that I was just mentioning. So my model overestimated the mileage by about 6.83, almost 7 miles per gallon. So I didn't do as great as I would have liked. So that's about it for my summary of the review of regression that you should have seen in your previous class. I hope you found this helpful, and our next video is going to be about inference for simple regression.